Lesson 4. So question 4 is about radioactivity. And we're looking at radium-226. And it says radium-226 emits alpha, beta, and gamma radiation. Figure 2 shows how the activity of radium will change. So this is a standard half-life graph. And we have to determine the half-life using the graph. Okay, so these are pretty straightforward. We have 2 marked. The problem with this one is though, I'm going to zoom in so you can see. I've come across this question before, I've marked this question many times. A lot of students always think that starts at 180,000, but you can see it's actually the square after 180,000, which is just particularly upsetting and annoying from your exam board, but they do like to try and catch you out, especially on these higher papers. So what we should be doing is working out exactly what that number is. In order to do that, as with any graph, we just need to figure out the scales. So in order to figure out scales, what you do is you count how many squares you've got between a certain area and how many that number of squares represents. So in this case, we've got, as you can see, between here we've got 1, 2, 3, 4, 5 squares. So we just write this on. So 5 squares, and that's equal to 20,000. Because the difference between these two numbers is 20,000. So 5 squared is 20,000 becquerel. So we can use that to figure out what 1 square is. So 1 square is, so if you divide that by 5, you get 1. So we have to do the same with this side. So 20,000 divided by 5. So again, even if it's easy, get the calculator out. 20,000, checking your zeros, divided by 5. So each square is worth 4,000. So 1 square is worth 4,000 becquerel. So that is our scale on that side. So as you can see, for this one being 1 square above, it's 184,000. So we've got 184,000 is our starting rate. Okay, we should work out the scale on the bottom as well, but we'll do this side first. So what we do on a half-life graph is we find half of the original sample. So we have to find half of 184,000. So if we just divide that by 2, again, I should have the calculator up, even with a simple 184,000 divided by 2 is 9,2,000. So that becquerel is where we're going to draw our half-life. So each of these squares is worth 4,000. So it would be 84, 84, 88, 92 should be there, and we should work it backwards as well. So 10,000, 96,000, 92,000. So it's that's here is where we're going to draw our line across. So we're just going to get a ruler. You'll draw a straight line. So you can't see that, I'm using a ruler on there. And then where this hits is where we draw a line down. So that is hitting on that square there, making sure to draw it really straight and that it follows that line perfectly. And we are going to have to figure out what this line is there. So the way we do that is we have to figure out the scale on this axis as well. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares. So 10 squares is equal to 1,000 years. So 1 square divided by 10, so we do the same to both sides, is equal to, well, I'm pretty sure we could do this in our head, but again, even with everything, just checking on the calculator. So we've got 1,000, we're going to divide it by 10, is 100. So 1 square is worth 100 years. So we have got our 1,000, 1,100, 200, 300, 400, 500, 600. So that is 1600 there. And that's how we work out our half-life. So our half-life is just whatever that goes to. So our half-life is 1600 years. Radium was discovered by Marie Curie in 1898. The notebooks she used were contaminated with radium-222. We know radium-222, we've just done the half-life. So half-life is 1600 years. So that is the amount of time it would take for the sample to halve. The notebooks are still hazardous. Explain. So let's say why. Why are they still hazardous? Well, if we figure out how many years ago that was, so we're currently in 2022, and we take away the year that she was using the notebook, so 1898. How many years ago is that? One. Try again. So 2022 minus 1898. So that's 124 years ago. So 124. So 124 years ago. So one half-life is 1,600 years. So we're nowhere near a half-life. So the explanation why is, so we are not yet close to one half-life passing. So therefore, the activity of the sample, but it won't even have half, so it will not have decreased by much. So we're not yet close to one half-life passing, so the activity of the sample will not have decreased by much. So that's why it's still hazardous. Next question. Explain how the properties of alpha, beta, and gamma radiation affect the level of the hazard. So, dangerous. Why is it dangerous? It's dangerous because radiation is ionizing, cause mutations, leads to cancer. At different distances. You know the alpha, beta, gamma. So you've got your most penetrating, most ionizing. You've got your least ionizing. Alpha is the least penetrating, and gamma is the most. So alpha is the most ionizing. It will cause the most damage to cells by removing more electrons because it's a bigger particle, but it's not very penetrating, so it gets stopped very easily. It can't travel very far in air, and it's blocked by skin or paper, so it's not very dangerous at a distance. Gamma can travel long distances. It can travel over a kilometre in air, but it's not very ionizing because it's a very it's an EM wave, so it's not like a large particle hitting into something. However, it is still ionizing, and beta is just in the middle. It's moderately ionizing and moderately penetrating. So we have to explain these properties at different distances. Let's give this a go. So let's start with alpha. So alpha radiation is the most ionizing, but can only travel short in air. it is also the least penetrating form. I should possibly make it look like the word form. That was like from of radiation. So alpha radiation is the most ionizing, but can only travel short distances in air. It is also the least penetrating form of radiation. So is very dangerous at short distances, but not dangerous over longer. Okay, so we've done alpha. Let's go to the other extreme. Let's go to gamma. So gamma radiation, you probably noticed whilst writing the alpha one there, I sort of lost my flow a little bit, and at that point you just need to read what you've written back to yourself and then go back to the question and get your head around it. Just don't keep writing, because otherwise you will go off on a bit of a tangent, and what you write might not be linked to the question. So gamma radiation is the least ionizing, but can travel long distances in the air. It is also the most penetrating form of radiation, so is dangerous. So is the most dangerous at long distances. And that's because, let's put in brackets, where alpha and beta would have been stopped. Yeah, because it is ionizing. It's just not very ionizing compared to the other two, but at long distances, it's going to be the most dangerous one, because beta and alpha won't be able to travel those long distances anyway. So if it's the only form, it's going to be the most dangerous at long distances. So let's have a look at our question. Explain how the properties of alpha, beta, and gamma has at different distances. So we've talked about alpha, we've talked about gamma, we've talked about them being ionizing, we've talked about them being poorly penetrating. The only thing, and we talked about the distances as well. So the only thing we need to do is we just need to add in the beta. So beta is, we can use this as a comparison one. So it's less ionizing than alpha, but can travel further in air. It is more ionizing than gamma, but cannot travel as far in air. It is moderately penetrating. It can travel. It's stopped by aluminium. So beta is less ionizing than alpha, but can travel further in air. It is more ionizing than gamma, but cannot travel as far in air. It's moderately penetrating. So it is the most dangerous form over middle distances. Okay, I think we've covered that out. We've got everything in there. I've had to sort of squeeze my writing down. It's still legible. I think the examiner could still read it, which is important. If not, and I got to the point where I was totally running out of space, I would just go the extra space in the back of the paper, which is always there. Again, read your answer back, or do what I do, and you're constantly checking throughout to make sure that you've mentioned these points. All right, that's the end of question 4.